generalized visible subsets.
Okay, just a sec. Let me just say hi, introduce you for a sec. So, well, Atul, you want to do the honors?
Okay, so it's our pleasure to introduce SnehaChaubey, who is a professor at IIIT Delhi. Sneha was my junior at Urbana-Champaign. I think we overlapped for about 6 months, right?
Yeah.
6 months to a year.
Yeah, 6 months. Yeah. 2000. Yeah.
Right. So she worked with Professor Alexandru Zarescu for her PhD, and then you were at Göttingen, right? For a year, and then she came back to India and joined IIIT. So today she'll be talking on generalized visible subsets of Z2. Thank you.
Thank you, Atul, and thank you, Gaurav, and Krishnan is not here. But thank you all for giving me this opportunity to speak here. And please interrupt me as and when you want, and if you have any doubts or comments. And yes, thank you so much. So yeah, so the topic is generalized visible subsets of Z2. We start with the definition of Z2. So what is Z2? Z2 is just the tuples of integers. And here I have a picture where I've just plotted all the in a big square, 20 cross 20, yes. Well, 40 cross 40, all the integer points. So now a brief introduction on what is a visible lattice point. So visible lattice point these are all points which are visible from the origin. So that's just the basic definition. So a point is a visible lattice point if it is visible from the origin, and hence the name visible lattice point. Now geometrically these points lie on the straight lines passing through the origin, right? And if a point is visible and it lies on the line L, let's say, then there is no point of, then there is no lattice point lying on L between the origin and the point. Right? So it has to be visible. So there shouldn't be any other lattice point lying on the line joining origin and the point. And any such line which will have a visible point on it should have a rational slope. So that is also easy to see. So if you have an integer point lying on a straight line passing through the origin, then the slope should be rational. Okay, and so we collect all such visible points. So, and we say that we call that set as V. So we say that V is the set of visible points through the family of lines y equals qx, where q belongs to, q is a rational number. Okay, so, so that's a picture. So you're drawing all straight lines with rational slopes passing through the origin, and the green dots, so the first point on the line will be a visible point, and rest all other integer points on the line will be invisible. So the green dots represent the visible lattice point, and all the red dots represent the invisible lattice points. Okay, and here is another picture. So so this again is the set of all visible lattice points. Now, what are the generalizations of V? So there is nothing special about family of lines, right? And one can replace the family of lines by any other family of curves passing through the origin. So the obvious next set of families one would be looking at could be y equals qx to the power b. So for b equals 1, you have the straight line. And now if you just generalize that, if you have a parabola, it would be y equals qx square and so on. So the next set of families one would be looking at is y equals qx to the power b. And for these curves, the visible points would be defined in a similar fashion. So what do we say? So we say that the visible points must lie on one of the curves from this family, and there should not be any other point of the integer lattice on this curve between the origin and the visible point. Okay. So basically it's the same definition, except that instead of straight lines, we have these family of curves, right? So Q is not fixed. You have, so as Q varies, you have all these curves, and now a point will be visible if there is no other point of Z2 which lies on any of this curve between the origin and the point. Okay. Now, well, for the case of straight lines, and we have symmetry, and we will also, so when we see, so there'll be more generalizations later where we will have non-symmetry, and for those cases we are going to restrict our attention only to the first quadrant. Okay, so as I said, this is the generalization. So we denote the set of visible points along these families as V subscript B because it depends on B. And as you can see, if you take B equals 1, then it's just the usual visible lattice points. Yes, so here is a picture.
Sorry, Sneha, can I ask a question?
Yes.
Are the XY also on lattice?
Sorry?
So they are on the lattice and B is fixed, right?
B is fixed, right? B is
And
fixed.
the lattice is also fixed, right?
Yes, so we are looking at all these curves y so let's say b equals 2, right? So we are looking at all these parabolas y equals qx square for various values of q on the integer lattice, and then we are saying that an integer point which lies on this parabola, visible lattice point, if there is no other lattice point lying between 0, 0 and this point
on the parabola,
right? If b is equal to 2.
Okay, thank you.
Any other questions? Okay. Now, there are various generalized. So, the picture which you see here, so this is a picture of the invisible lattice points. So for b equals 1, you have you have the picture on the rightmost corner. Well, that's the leftmost corner up. And then for b equals 2. So what one can observe is as b increases, there are the density of visible lattice points increases, right? At least that's what the picture says. Okay, so that brings us to the question of density. So we just observed that the sets VB appear to be more dense as B increases, right? And so we want to measure this density. There are various ways to measure density. We will be using this notion of density. So the natural density for any subsets S of Z2 is defined as, so you're looking at the cardinality of the, so number of points in a square divided by the area of that square. So that's the density. Now, this is age old. So we already know what is the density of visible lattice points. It's pi square over 6. And so this generalized notion of visibility for these curves is not something which we have invented, but this was done by Goins, Harris, and a couple of other authors in 2017, very recent, where they already looked at the density. So they computed density to be 1 over zeta b plus 1, where b is a natural number, and zeta is your classical Riemann zeta function. So as expected, so for b equals 1, you can see that it's just 1 over zeta 2, which is pi square over 6.
So Sneha, it should be 6 over pi square.
Yeah. Sorry about that. Yeah, thank you, Atul. So so density of b is 6 over pi square, not pi square over 6. It's 1 over zeta 2. Okay. And so if the density of VB is computed to be 1 over zeta b plus 1, now you know that zeta is a decreasing function. So the density should increase as b increases. And in fact, as s goes to infinity, zeta s tends to 1. And therefore, the density approaches 1 as b goes to infinity. So now if you vary b, then it looks like the density approaches 1. Okay, so before I get to the next slide, so it seems that there are more since the density approaches 1, it looks like almost everything is a visible lattice point. But well, there are gaps, and what can you say about gaps? So the question is that, well, are there arbitrary large gaps in the sets VB? So what do we mean by this question? So basically we want to see whether if you're given a number, then can we find a square of side length that number so that all the points inside that square are not visible, are not in VB, right? So we want to find holes basically. So and we want to see whether there are arbitrary large holes in this set VB. Now, because the density approaches 1, it seems unlikely as B increases. So, okay, what happens? Let's do case by case. So, what happens when B is equal to 1? So, in the classical case, B equals 1, which is the set of visible lattice points. Herzog and Stewart, they used a notion of prime matrices and the Chinese remainder theorem to prove the existence of invisible squares. So the first invisible square, so by first I mean the one which is closest to the origin, is what I have here. Okay, so they discovered this as a square which had no visible points inside, and this was the second invisible square. So so this is a square of size 1, and this one is 2. Now, there is this story that, so Wolfram, Stephen Wolfram, he claims to have found the closest 4x4 invisible square, which is located approximately 13 million units from the origin. Okay? And as of now, at least what I know, we even don't know the closest n cross n invisible square for n equals 5 or beyond. So this is still open. Yes, questions from this slide or before? Okay. Yes, some more results on gaps. So Leshram, Shanta is also here. Today, Leshram and Luca in 2015, they gave some bounds on the location of invisible squares in Z2. And Bach and Huck, they gave a simple proof of arbitrary large gaps for B equals 1 using the Chinese remainder theorem. And in 2019, few authors, Flores and his collaborators, they came up with a proof for the arbitrary large gaps for the general case B greater than equal to 2. So they showed that there are in fact arbitrary large gaps for B greater than equal to 2, but their proof is kind of messy in the sense, at least it extends for 3-4 pages. So, so in a paper which we submitted with my co-author Ashish Pandey, we showed that we gave a simple proof for the existence of arbitrary large gaps in this general case B greater than equal to 2. And about the location of invisible squares, we don't know. Very little is known, even for the general case B equals 2 or above. Okay, so slight detour. So so after visibility, yes.
I don't understand the difference between gap and invisible square. So.
Okay, so so when I say so gaps is basically invisible square, but there are two questions. One is where are those squares, invisible squares located, and the other is what can you say about the size of those gaps?
Okay, okay, thank you.
Yes. So so as of now, so whatever I said about visibility, you can notice one thing is we are only talking about visibility from the origin, right? Whether a point is visible from the origin, either it is on the straight line or it is on the curves y equals qx to power b. But one can slightly twist this question, and a natural problem can be to study distribution of lattice points which are visible to more than one point, so which are visible to more base points simultaneously. So now instead of just talking about visibility from origin, one can talk about visibility of lattice points from more than one point, right? So, we, along with my, so I and Albert Tamazian, and along with my advisor Rescue, we looked at this problem for the usual visible lattice points in this paper called Lattice Point Problems Involving Index and Joint Visibility in 2019. And very recently, Meng with his co-author Liu, they did the same problem for visibility, visible lattice points along curves. So the visible lattice points which I just defined, yes, for these family of curves y equals qx to bar p, they're looking at simultaneous visibility in this paper. Okay, so well, again, there is nothing special about looking at these set of families, right? Y equals qx to bar p, and in fact, one can generalize this, and one can define a notion of visibility for polynomials. So, quick definition. So, for a fixed vector a, so that an is non-zero, we define a polynomial Pax of degree n, and so for that polynomial we define a family. So now for that, in the previous case the polynomial was just y equals q times x, x to the bar b, but now we are taking a general polynomial. It's just that. Okay, and similarly one can define a point AB to be f visible if there is a curve in this family such that if a point lies on this curve, then there is no other lattice point on the curve between the origin and the point A comma B. It's the same definition, but instead of those curves, we have a general polynomial and we have this general family. Okay, and let us denote V of A to be the set of visible points with respect to this family f of A. Okay. So in the same paper, we made this conjecture that the density of V of A, so this density is exactly by the definition of density I gave before. So counting number of visible points in the square, dividing by the area of the square. So the density is in fact exactly equal to 1 for any A which is not 1, 0, 0, 0. So when A is equal to 1, 0, 0, so if you consider the vector A equals 1, 0, 0, can anyone sitting here tell me what is the polynomial? Maybe one of the students. So in the conjecture, you can see that I missed 1, 0, 0, 0, right? So if A is equal to this point, then what curve are we talking about? What family of curves are we talking about? Okay, so so you can see, so if A is 1, 0, 0, then it's just x, right? So the polynomial is just x, and then you're only talking about straight lines. So in the case of straight lines, you know what the density is. Yes, the density was 1 over zeta 2, right? Okay, so for any other vector 1, 0, 0, we conjecture that the density is exactly equal to 1.
Sneha, there is a question from Saroj Malik. What about the vertices of invisible squares?
Okay.
But I don't know when this question was asked. So maybe.
Okay, maybe I can take it. Oh, yes, the road says something. Are these invisible? No, these are not. Well, these are not visible. Yes, these are invisible.
Thank you.
Thank you. Thank you. Okay.
Sorry,
So,
can I ask a question about this conjecture? You
yes.
excluded 1, 0, 0, but what about 0, 0 up to 1? That would be the previous case that you discussed where you said the density is the inverse of the zeta b plus 1, right?
So
Because
when
that will be x to the power n only, y equal to q x to the power n, right?
right. Oh, sorry. So I should have yes. So so that's exactly so that is covered in this. Yes. So when n is equal to 1, it's just the straight line, and for any n, it's
No. I mean arbitrary
theta.
n, but an is equal to 1 while the other low a n minus 1 up to a1 are 0.
Exactly. So
That's
then
the
that's
previous
just
case,
to the
right?
power n, right?
Yeah.
Yes. So yes. So for n equals 1, that's 1 over zeta 2, and for any arbitrary n, it's 1 over zeta n plus 1.
Yeah, so then the density is not 1, right? So this
Yes,
conjecture,
and therefore we have not. So we've not considered that vector point.
but then you have to exclude that as well, right? You have only excluded 1, 0, 0, 0. You have to exclude 0, 0, 0 up, comma, last entry is 1.
No. So okay. So this will include all cases, right? Because if you have a subscript n equals 1, and if you take little n equals 1, then you have the straight line,
That is true. I'm saying take any arbitrary n, say n is equal to 6.
right?
And now I have a6 equal to 1 while a1 up to a5 are all 0. That's also
Yes.
covered in the previous case, right?
Yes. So that curve will be y equals q times x to the power 6, right?
Yes.
So for that you have 1 over zeta 7.
So density is not 1, that's all.
No. But we've already excluded it. So, okay, my vector, so the way I've defined my vector is slightly in an opposite. So if you look at the top of the screen, what is my vector? Vector is a sub 10 up to a1.
Yeah.
Well, I mean, maybe just a question of it's a notation. Yeah, notation is a bit
Okay.
confusing.
Right? So it's, yeah, okay. So you were thinking it's a1 up to an. Sorry. No. So the way I've written my vector, it's in an opposite way. So is this clear? So therefore we have covered all.
Yeah, thanks.
Okay, thank you. Okay. So here is a picture of various curves. So this is V1, 1. So V1, 1 would be the curve x square plus x, right? So that's a plot of all visible lattice points. V2, 0, 15, for example, would be a curve 2 times x cube plus 15x, right? And similarly, for example, 60413 would be 6 times x to the power 4 plus 4x squared plus 13 times x. And similarly, you have this. So it looks like it's at least numerically, and that's what we thought. So it seems that the density is 1 for all these families. Okay, so some more numerical computations. So this is what was the, so these are the these are the 4 polynomial families whose curve, whose picture you just saw. And for these, we just computed these densities. So you can see that it looks like it approaches 1. Now it's still a conjecture. It's open for all values of a. So even for x squared plus x, one cannot, we were not, at least we were not able to show that the density is exactly equal to 1. Okay, so So let's see what one can do for VB. So for VB, as was pointed, so for VB is exactly 1, 0, 0, right? So for VB, we have that x comma y is in VB if and only if this generalized GCD is equal to 1. So for the usual lattice points, for the usual visible lattice points, you know that a point is visible if the GCD of the coordinates is equal to 1, right? Likewise, here also we have an arithmetic criterion in the form of GCD, but GCD is now generalized. So if you have a point x comma y is in VB, if and only if this GCD is equal to 1. So this is defined. So this is the usual GCD for B equals 1, right? And so because you have this nice arithmetic criterion, you can easily compute your density, and hence one gets the density to be 1 over zeta B plus 1. The problem with any general polynomial is that you don't have this beautiful arithmetic criterion which will help you to explicitly compute what the density is. No such criteria is known for other polynomials. But what one can do is at least one can give a lower bound on this density, because a sufficient condition for a point x comma y to be in V of A is that the GCD of P of x comma y should be equal to 1. So we don't have a necessary condition, unlike the case VB, but at least we have a sufficient condition which will help you in giving a lower bound. So because of this condition, so basically you're counting all those x, y's for which the GCD of P of x comma y is 1. Because of this, one can do some quick number theory, use some generalized Chinese remainder theorem, and show that this and can get a lower bound for this density in terms of this infinite product. And this function, so sorry, this should be yes. So density of VA is always less than equal to sorry, density of SA is less than equal to density of VA. So and density of SA is given by this, where f of d is number of points A in from 1 to D, so that P of A, D divides P of A. And again, this function f will depend on A, the vector A, and it can be calculated explicitly in some cases. So for example, if you take your vector A to be 1 comma k, so that is your polynomial x to the power, that's x squared plus k times x, right? If your vector A is 1 comma k, the polynomial is just x squared plus kx. So in that case, you can see that f of p is given by this, is 1 if p divides k, and it's 2 if p does not divide k. And because you have an explicit value of f, you can easily compute that product above, and it can be written in this form. Okay. Just checking. Are you with me?
Yeah.
Okay. Okay.
I think you stopped sharing.
Is my screen visible?
Yeah, everything.
Yeah, we can see. Yeah.
Yeah, actually, yeah. In one of the other devices, I just my internet got cut off, so I thought that again on this as well, internet got cut off. Okay, good. Okay, so little more theory on what is happening with the next simplest case, which is v of 1 comma 1. So quick recall. So we know everything about y equals q times x to the power b. Now we just want to deal with the simplest example, which is x squared plus x. So the problem here is, so x squared plus x, so if we just plot a picture, so we are trying to count those points x comma y which do not belong to V of 1 comma 1. And if we plot a picture, that's how it looks. So what it says is that although the number of y's for most values of x is close to 0, one can see that there are occasional spikes, right? And because of this, getting a proof is not easy for the density, even in the simplest case, x squared plus x. Does it make sense? Okay. So, so now so this was, so just before this slide, so whatever we covered about visible lattice points, about generalized visible lattice points, so that was from an arithmetic point of view. But now what I'm interested in is I want to study these lattice points in a more set-theoretic manner as a set. And I want to see, we want to study some properties, both in a topological setting as well as in an ergodic theory setting. And we want to extract information about these sets as much as possible. So, so in the remaining lecture, we are only looking at VB. So whatever new results we'll see, that will be for VB and not for these generalized polynomials. So is the story clear? So up until now, we had this notion of density. We saw that for the usual visible points, it's just 1 over zeta 2. For y equals qx bar b, is 1 over zeta b plus 1. And for general polynomials, we see that it is 1, but we don't have a proof for that. Now we want to study this set of generalized visible lattice points, VB. So we are so the family of curves is y equals qx to power b. We are not looking at polynomials anymore, and we want to study them from a different point of view in terms of topological and ergodic theory. Okay, so so there are these 2 points of views. One is the diffraction point of view, and the other is the topological point of view. So maybe I'll briefly tell you some of the notions which we will be using. So so basically these are notions from this area of aperiodic order of lattices. So there is this notion of Delone sets, which is nothing but, so these are basically some description of some mathematical description of atomic arrangements. And so basically you have these, so in crystallography, for example, you have, you want to model, you want to give some mathematical models to various atomic arrangements. And there you come across these Delone sets, which are uniformly discrete and relatively dense. Now, model sets are some special types of Delone sets, and they have rich spectral structure, and they in fact model the quasicrystals, and they are very well studied, and a lot of so things about model sets. So people know a lot about model sets because they are used to model quasicrystals and so on. So these model sets are a type of Delone sets. But now if you relax one of these criteria of relatively dense, then what you come across is you come across a weak model set. Now, weak model set is not very well understood as their model set's counterpart. So, okay, so for those of you who might be interested in convex, some group theoretic, group theory and so on, it's something like, it's, so one can have an analogous view about thin groups and arithmetic groups, just like for those of us who would be interested in that. So for example, a lot of things is known about arithmetic groups, but not many things are known about thin groups. But there are several examples of thin groups coming into picture. So it's like that. There are a lot of things understood about model sets, but not many things are understood about weak model sets. But there are several examples of weak model sets which we come across. And some of the examples, the earliest example was is a set of square free numbers. So this is an example in one dimensional. So a square free number is a number such that no prime square divides the number. And then in two dimension, so square free numbers and then k free numbers in one dimension. And in two dimension and more, you have the visible lattice points V. And this VB, which is a generalized visible lattice point, is also an example of a weak model set. So, because the set theoretic properties of VB matches with visible lattice points and so on, we would want to see the properties which have been studied for visible lattice points in this under this umbrella of generalized visible lattice points. Okay, so some properties. So I'm just going to reiterate. So VB is not a Delone set because it is uniformly discrete. Now, so maybe just to understand what this uniformly discrete and relatively dense means. So for example, Z2 or Z2 is a uniformly discrete set, right? You can see that there are uniform gaps in Z2, and so VB is not a Delone set because it is uniformly discrete, and it is because it is not relatively dense. It's not a model set or a Delone set. So relatively dense, not relatively dense means it has arbitrarily large gaps. So therefore, VB is not a regular model set, and in fact, it is a weak model set of positive density. One more property one can identify is that there is this relation. So basically, the set of the usual visible lattice points will lie in the set of two generalized visible lattice points. So whatever point is visible for for the family y equals qx, it's also going to be visible for the family y equals qx square. Similarly, y equals qx square family would be visible for y equals qx cube. So this inclusion is clear. Okay, and the other thing is that this group acts transitively on the generalized visible lattice points. So this group is SL2Z intersection upper triangular matrices, and this acts transitively, and one can see that one can partition the set of all lattice points as a union of these G invariant sets. Okay, so for example, maybe I'll just give you a quick analogy with the usual visible lattice points. So when B equals 1, you see that the group SL2Z itself acts transitively on the usual visible lattice points. And in that case, you can see that one can partition the set of lattice points as a union of visible lattice points, right? Because that's clear, right? So if any, so does this make sense? The last point. So for B equals 1, because of the simple GCD criterion, one can see that you can partition the set of integers in the as union of visible lattice points. Okay, and for VB, this is the group which acts transitively. So, so that's these are some set theoretic properties of VB, and now we want to study the diffraction. We want to study the mathematical diffraction theory. So, what does the mathematical diffraction theory mean, and what is all this here, and what does it make sense in the setting of visible lattice points? So basically, so mathematical diffraction theory is concerned with the measurement of kinematic diffraction. And what is kinematic diffraction? So if you remember from physics, what is kinematic diffraction? You have a screen and you have light passing through the screen, and then you have on a far field object, you want to see how does the spectrum look like and what is the intensity and so on, right? So how does the visible lattice points come into picture? So now your screen, imagine your screen consists of all these lattice points with holes at these visible lattice points, okay? So you have Z2 as your screen and you have holes at these visible lattice points, and now you want light to pass through it. And once you have the light passing through it, in a far field object, you want to see what is the image, what is the spectrum, and what is the intensity at each point, okay? So I'm just giving you an intuition of how all this makes sense in this theory of visible lattice points. Okay, okay, so so this is just some mathematical theory of how you compute the intensity. So the intensity is measured using the Fourier transform of the function f. So so we basically call it as the autocorrelation measure. Okay, so I'm just quickly going to skim through it because this is all little technical theory. So and you compute the Fourier transform of this, and if it exists, it's called the diffraction measure, and that is how you're going to compute the density. Okay, so so usually what happens is that for mathematical diffraction theory, one has to formulate the. So if you look at this diagram for translation bounded measures, so what happens that the Fourier transform of a tempered distribution is a tempered distribution, but it's not necessarily a measure. So if it is not a measure, then it doesn't make sense. So this sense of taking the absolute square and so on doesn't make sense. So therefore, in order to, so from f to f hat square, if you want to compute the intensity, you want to compute this function, but this does not make sense for a tempered measure. So instead of taking this path, one takes this path, and here, therefore this diagram. So okay, so so for visible lattice points or for generalized visible lattice points, you define this measure, and which is called the autocorrelation measure, and one can compute this eta z explicitly in terms of this function here. Okay, so so now if we take the Fourier transform of this measure, then you see that you get this discrete sum over the intensities, and these intensities, if you just believe to what I said in the previous slide, and if you just look at this sum, then you see that this sum is supported only on rational points with square free denominator. Okay, so this is a discrete sum, and what it basically tells you is that the intensity is a pure point spectrum. So it's a discrete pure point spectrum instead of continuous. So because this intensity is supported at these discrete sets, right, where density where the points of Q2 have square free denominator. So so what this means is that the diffraction spectrum of the set of visible lattice points is a pure point spectrum, because this is a discrete, because this is supported on a discrete set. So this was important. So why all this is interesting? Because there are two things. One, that the diffraction spectrum is a pure point spectrum rather than a continuous spectrum. And second, because the intensity is very easily computable. So you can see that it has a nice formula, and one can now explicitly compute this finite product, right? So these two facts make it an interesting thing to study. So, and this happens even for the usual visible lattice points. So for B equals 1, you get a pure point spectrum and your intensity. So you can just take B equals 1 and you get this as the intensity. Okay, so maybe towards the end of this these slides on diffraction spectrum, I would want to quickly tell you why has this been studied and what has been the history and development of this problem. So Schroeder in 1982, he was the first guy to investigate the spectral properties of visible lattice points, and he observed numerically that the spectrum is continuous and it has continuous diffraction components. But in 92, after 10 years, using some Mobius inversion calculations, Mosheri, he argued that the diffraction should be pure point. But his proof was not complete. I mean, it was complete, but he did not come up with definite error terms. And after 2 years, Bach, Grimm, and Warrington, they used an analogy of an optical diffraction experiment. And with some further calculations, they supported Mosheri's claim. And only in 2000, Bach, Moody, and Peasants, and then in 2013, Peasants and Huck, they extended these results of pure point spectrum for visible lattice points and k-free integers with precise error estimates. So up until then, they were not able to come up with explicit error terms, but using the results of Mirsky on R-free integers. So these are the two papers of Mirsky. They came up with a precise asymptotic formula with good error bounds and showed it for visible lattice points in 2000 and in 2013 for k-free integers. Okay, so questions? So where is the number theory? Yeah, sorry.
So you still have some more things to say, no? I'll ask at the end.
Okay.
While you are at the page of history, let me just tell that Indian Society for History of Mathematics has its annual conference via Zoom from 20th to 22nd December. And you have to register before 12th of December and also tell if you are ready to give a talk. And you can open the website http indianshm.org and register and submit the abstract of your talk and all that while you are at history page.
Thank you, Professor Jeet. Okay. So this was about the diffraction spectrum. The next is, so usually when we want to study about the set theoretic properties, there are two things. One is the diffraction point of view, and the other is the topological point of view. So which is also the dynamical system point of view. So maybe I'll briefly try to motivate where did this dynamical point of view came into existence and how all this began. Basically, why did we want to study the dynamical systems point of view for these visible lattice points and so on. So it all began with, so Sarnak, he conjectured a statement involving the Mobius function. So he said, which basically talks about the randomness of the Mobius function. So the statement isn't, it's a kind of ergodic theory statement. It involves this zero entropy continuous map T of a compact metric space is Mobius disjoint if this limit, so this should be equal to 0, sorry, it's missing here. So this limit n goes to infinity, 1 over n, summation n less than equal to n, f of this equals 0 for every f in C of x. So this limit is equal to 0 is what was conjectured by Sarnak. And in fact, if this is difficult to understand or decipher, then basically, if you consider rotations, if your T is a rotation map, then this leads you to the Davenport's result, which basically is that summation mu n times e to the power 2 pi I n alpha is equal to 0. Limit 1 over n summation n less than equal to n, mu n times e to the power 2 pi I n alpha is equal to 0 for every alpha in some unit interval. So, and in fact, this is a very general conjecture because again, for some special value of t, you can translate this sum in terms of the prime number theorem. So this is equivalent to the prime number theorem for a specific map T. Similarly, you can see this as a form of Dirichlet's primes in arithmetic progression. If you take again a translation, I think T should be a translation, T of x should be x plus 1, something like that. Okay, so this was a general conjecture, and in fact, this is interesting because also because Chavulus Conjecture, which again talks about the different correlations between the Mobius functions. So this is the Chavulus Conjecture. So if you have these numbers k1, k2, kr, and these powers are either 1 or 2, so it's either mu or mu square, then this is equal to 0. So this is the Chavulus Conjecture. This implies the Sarnak's conjecture. So anyway, now where did all this come? So what one observed that these properties of the Mobius function can be investigated by looking at its square, mu square, which is the characteristic function of the set of square free numbers. And hence, so in order to study this, one wanted to study mu square, and hence one was interested in studying the dynamical and spectral properties of square free integers. And later on, it was observed that the visible points of Z2 also have similar dynamical and spectral properties as square free integers. And in an ongoing work, we see that the generalized visible points, VB, also have similar dynamical and spectral properties as V. Okay, so what do I mean by this dynamical property? So for that, I will have to define some notions. So you have this XV, which is also called as the discrete hull. So for example, so for us, V is VB. And if you take V, so V is the different, so for some V is the visible lattice points. Sometimes it's the square free integers. And similarly, in our case, it's the set of generalized visible lattice points. So this is the discrete hull of V. So it's basically a translation closure of this translated set of visible lattice points. So Herzog and Stewart in 1971, they came up with the characterization of this discrete hull. And they showed that this discrete hull is basically the set of admissible subsets of Z2. So one can explicitly see what this is. This is nothing but the set of admissible subsets. So what is admissible subset? It consists of subsets with A subscript P, the cardinality of A subscript P less than P squared for any prime P, where AP denotes the reduction of A modulo P Z squared. So basically you're looking at all the residues modulo P except one. So if you have a subset which consists of all residues except one, then its cardinality is going to be less than P square, right? It's in Z2. So its cardinality is going to be P square, less than P square. So in fact, they saw that this XV is exactly equal to this set of subsets, right? Okay, so you can already see that this XV is a set of subsets. It's not, so for different values of T, you have these T1 plus V, T2 plus V, and now you're taking the closure, right? So this XV is nothing but this A, which is a set of subsets. And Sarnak in 2010, he characterized this XV for square free integers. And then in 2014, Bach and Huck, they characterized this discrete hull for K free lattice points. And they also look at this B free lattice points. What is a B free lattice points? So basically, it consists of lattice points. It consists of pairwise co-prime integers satisfying this. So for a special B, you can see that this is nothing but the K-free lattice points for a special set B. So B-free lattice points is a generalization of K-free lattice points. And as was expected, because it's true for B equals 1, so it should one should be able to characterize for general B. So in an ongoing work, we characterize this discrete hull, and we see that this discrete hull is nothing but again the set of admissible subsets where AP is less than P to the power B plus 1 for any prime P, and AP denotes the reduction of A modulo P comma P to the power B. Okay, so why is this discrete hull important? We will come to that in a moment. But before that, so another topological property which I would like to define here. So suppose you have a subset of a lattice given a radius rho and a point T in the lattice. The rho patch is defined as this. So it basically, you're looking at all those points which such that if you translate it, then it belongs to your subset and it should be inside the ball of radius rho. Okay. So that's one rho patch. Now, if you vary your T, you get a different set of rho patches. Okay, and you denote that by A rho. And let's call n rho as the cardinality of these different sets of rho patches. Then using this notion of rho patch, you define a limit such as this, which is called as the patch counting entropy. So all this is like is a common thing in topological dynamics. So this is a patch counting entropy. And in fact, using some kind of variational principle, one can see that the topological entropy is same as patch counting entropy. So entropy is basically measures the complexities of a system. So I mean that's the intuitive idea for those of us who do not know much of topological dynamics. So now coming back to the interesting theorem here. So we have defined two concepts here. One is the discrete hull, and the other is this entropy, the patch counting entropy, which is nothing but the topological entropy. So Bach, Huck in 2014, they showed that this discrete hull and this space is nothing but a topological dynamical system, and they were able to show that this is ergodic, and the topological entropy is equal to 1 over zeta 2. So when V is the set of visible lattice points. So, and in an ongoing work, we show that this space is a topological dynamical system, and it has a positive topological entropy equal to 1 over zeta B plus 1. Although, yeah, we have not been able to show the ergodicity part, but because, yeah, because we need some help from an ergodic theorist to deal with this part. So, and in fact, this theorem, which Bach and Huck proved for the usual case of visible lattice points, this theorem for the square free integers was proved by Sarnak some time back. So, yes, so I think I will quickly summarize, and that also brings me to the end of this talk. So, we started with this general notion of visible lattice points, where we first looked at the density. We first looked at the density of these, and we also looked at the density for general polynomials. And then we are looking at these two notions, one with the point of view of topology and the other dynamics, and the other with the point of view of diffraction. And only for this set of VB. So I think, I mean, there are like lots of problems here to investigate. One is we don't know anything. So this is just one set of families, right? We don't know anything about even for a simple polynomial like x squared plus x. And now like one can study these intensity problems and this dynamics problem for those visible lattice points as well. And in fact, maybe I'll just make one last note. So this, I think I skipped, I missed saying that. So this, just because a lot of number theorist friends are here. So this simultaneous visibility, which I discussed, where you have simultaneous, where you're looking at visibility from more than one base point. So this problem can be also viewed in hyperbolic geometry. So, and in fact, this notion of generalized visible lattice points makes more sense, more practical sense in hyperbolic geometry, because straight lines are the shortest paths for Euclidean geometry. But in fact, for the upper half plane, if you look at the hyperbolic geometry, then you have the geodesics. The geodesics are not straight lines, right? They are the semicircles and lines parallel to the y-axis. So for them, if one can define this notion of generalized visible lattice points, and then one can also study simultaneous visibility. So this is a problem which I'm currently like interested in, and if you have like thoughts or if you have interest in that problem, then please we could connect. Yes. Thank you.
Yeah, I have a couple of questions.
Yeah, Riddhi.
Nice talk. And let me, when you take density, you're taking squares because it's easier to calculate, but it should be the same if you take balls and, right? It should not change. Density is a bit.
Yes. This should not change. Yeah.
Another thing is how far
Yeah, it's easy.
how far did the conjecture go? I mean,
Oh, the conjecture just went not very far. We just could find the lower bound. Yeah.
okay, so the lower bound is.
The lower bound is given. Okay. I think
Sorry, I missed some of the things in between. I was blank.
Yeah. So we obtain the lower bound because we get this necessary condition of the
Yeah,
G
I saw that. Yeah.
polynomial
X, Y equals.
one. Yeah. So yes. So for explicitly, so I think, for example, for 1, 1, meaning the polynomial x squared plus x, we get something like 0.6 or a lot. Yeah. So that's best. We could
What
do.
about higher bound?
Sorry.
A bound from above?
This should be equal to 1.
Okay. It's already known, is it?
No. So numerically, that is what we.
Yeah, I saw your calculations.
Yeah.
What I mean is that you have a result for lower bound for one polynomial, but is there some.
Okay. Yeah. So for any general polynomial also we have a lower bound. I just showed it, but I mean it's a product, so it's for any function f. So now if you have a fixed function, maybe I can just pull up that slide again. Yeah. So this thing in the bottom, can you see?
Yeah.
Yeah. So this is the lower bound.
Okay.
For no, so again, this is the lower bound for this
One.
x square plus k times x.
Yeah.
So this represents the polynomial x square plus kx.
Ah.
Any general polynomial, this is the lower bound.
Oh, 1 minus fp over p square. Okay. I see. But what was the basis of this conjecture? Like, I mean, how did you think of making this conjecture?
Yes, so basically we started with finding the density explicitly, like
Oh,
computing the density.
okay, so
And because we were not able to compute the exact density, we then started looking at lower bounds, upper bounds in this. And I mean, so then we started doing some numerical computations of what the density should be, and the density looks like it is 1. And yes, so the best we could do is come with the lower bound.
okay. Thank you.
So Sneha, nice talk first of all. I had one question about the connection with diffraction theory that you said. So do you get some new zeta functions along the way, or is it Riemann zeta function itself that plays the role?
Yeah, it's just the Riemann zeta function which plays the role. Because, I mean, that's expected. Because, so in density basically features the density. The density has the Riemann zeta. But, I mean, I don't know what is going to happen for any other polynomial. Because this is just again y equals q x to power b.
The reason I'm asking is there is a very nice paper of Zagier from 1998 called Modified Bernoulli Numbers. And in that, he actually develops a theory of Bernoulli numbers analogous to, modified Bernoulli numbers analogous to the classical theory. And we extended it to polynomials. And we found that actually the corresponding result for the Fourier expansion of Bernoulli polynomials is actually something which is related to diffraction theory. So the reason I'm asking, and because you're having this generalized notion of GCD, so I was quite interested when you said about diffraction theory, because there are a lot of things. I mean, there is a parallel theory to that of Bernoulli polynomials, wherein there is scope of new zeta functions to come into the picture. So.
Oh, interesting. Okay. Yeah, I would want to have a look at that. Just to
So I'll
understand.
send you the paper where there is this connection.
Yeah, thank you so much.
Yeah, nice talk. Thanks.
Thanks. Yeah, and maybe I do not. Maybe just for I'm still like learning these areas, and many of these things are new to me also. But for those of us who are like interested in this is an excellent book. Like deals with a lot of these things. So
Yes.
in periodic order, and this guy Bach is the boss in this field. Yeah, he has lots of these results.
Okay, very nice talk, Sneha. One idea after another was just tapping from your slides. So, any further questions, comments?